check. Just a minute, guys. Let me figure out if I am out, if I am live properly or not. Awesome. I'm able to hear myself. It all seems good. Good. Good afternoon, everybody. Good afternoon, Ryan. Good afternoon, Ready to Win. Good afternoon, Akshat. Finally, Akshat is here from his own ID. Okay. All right. So, we have been discussing vectors, and yesterday the first half of the class was all about what kinds of exams can you possibly attempt with this preparation, what various exams lead you to, what kind of colleges exist, what is their rough hierarchy, what is the number in terms of percentage that you have to be in if you were to get a decent seat in a top rated engineering institute of this country. We saw these things in the previous class, and the other half of the class was spent on covering one operation, algebraic operation on vectors, that was scalar multiplication of vectors. I hope all of you have revised the previous 3 classes starting from Saturday, Monday, Tuesday. All these 3 classes are revised before you are sitting for this class. And if you haven't, then please do. I'm not saying you do not attend this live, but please make sure that you revise stuff. Good afternoon, Udit. Good to see you. Good to see your message. I wish I could see you guys also. Maybe we will arrange something like that, towards the end of the bridge course. For those of you who are interested, we can have a live session wherein you guys could also switch on your camera and we could interact, and then everybody, all of the audience could see. We could plan something like that. Good afternoon, Ryan. But for now, let's just continue with what we have been discussing, which is algebraic operations on vectors. We will continue that today. Before that, just a quick recap of I shouldn't say recap, because you can always go back and study whatever has been explained from the previous class on your own. Let me give you a small question to test your understanding. Okay. Let's say you have a vector A bar. Then how is... Okay, in fact, this is very simple. This is too straightforward. Yesterday, I explained you the concept of unit vectors, and I taught you how to construct any given vector from a unit vector. Unit vector is a representative of direction, right? We saw this clearly in yesterday's class. Let's do some reverse engineering. I shouldn't use the term engineering, because that is used for, when you are having a gadget and or let's say a software or something else which you have in your hand. You don't know how it is constructed, but then you can backtrack it. Like, you can look at the end product, then you can start analyzing its bits and pieces, then you can dig further and you can start breaking that product down, and then you can trace if you're able to trace the entire process based on which that product was built, that's known as reverse engineering. So we will do sort of reverse engineering today, reverse engineering on vectors. So yesterday I taught you, if you have a unit vector given in this direction, then you can construct any vector in that direction by just multiplying this unit vector with a suitable scalar. Let's say this unit vector is a cap. If you multiply this a cap with a scalar, then you can get any vector in this direction along this line. You can get any vector pointing in the same direction. It can be anything. So depending on the magnitude of your required vector, you can choose a certain lambda, and then if you multiply that with a unit vector, you will get any vector in that direction. So lambda was taking care of the magnitude, and this unit vector was taking care of the direction of this new vector, right? So what we will do now is, let me say I have a vector available with me in this direction. This vector is a bar. If I have the vector available, is it possible for me to get a unit vector in this direction, a cap? So this time the situation is reversed. I have a bar. Can I get a cap from a bar? Yes, we can. Akshat is right. If you have a cap, you can get a bar from a cap. If you have a bar, then you can get a cap from a bar, right? I hope you understand the difference between a bar and a cap. A bar can be a cap if magnitude of a bar is 1. This symbol is used for the magnitude of a vector, like the length of the arrow that represents the vector. If that arrow represents 1 unit, then this a bar can be a cap. But it's not a necessity that this a bar has to be a cap. It can be something else also. It can be of any length depending on its magnitude. Okay. So how do you get a cap? If we can, then how can we? Is there a mathematical formula? Can somebody type in? Instead of drawing the arrows, you can say bar. Instead of doing mod of a, you can just type mod a. So can somebody type the answer how to get a cap if you have a bar? Maybe people are struggling to type, so I will type it myself. A cap is nothing but that vector whose magnitude is 1 and direction is along a bar, right? So a bar has a certain magnitude. Let me write it like this. A bar is made up of its magnitude and direction. Any vector, as we have been repeatedly seeing, any vector is a product of magnitude and direction. Okay, so that is how your a bar also is. If I can get rid of this magnitude, or if, in other words, if I can make this magnitude as 1, then I can get a cap. Because ultimately a cap is that vector which points in the same direction as a bar, but its magnitude is 1. So how will you make the magnitude 1? If you divide this a bar with its magnitude, then you have to divide a bar with scalar quantity. What is that scalar quantity that you will have to divide it with? You will have to divide it with the magnitude of a bar, because then you will be dividing it with magnitude. So then magnitude will get cancelled, or in other words, it will become 1, and then you will only be left with direction. So the takeaway from this is, if I want a unit vector along the direction of a given vector, In our example, this unit vector was a cap and given vector is a bar. Okay, in our previous example. So if I have to get a unit vector along the direction of a given vector, then I need to divide the given vector the given vector with its own magnitude, and this magnitude is the scalar that Akshat is talking about in his response in the chat. What will happen if you visualize it? What will happen? Fine, this is regarding the mathematics, but if you visualize it, what will happen? We have seen, right, if you have a vector a bar and if you multiply it with lambda, then the vector will get resized, correct? Provided that lambda is more than 0, the resized vector will point in the same direction as a bar, but the length will change. Now if this lambda is less than 1, then what will happen? It will become lesser in size, no? Because in other words, you are dividing. It's something like you have a magnitude of 2, but if you multiply that with 0.1, then your magnitude will become 0.2, no? It will become lesser than 2. That's what I'm doing. In other words, I'm multiplying it with a scalar. I'm resizing it, but that scalar is less than 1. So you can also think of it as division, but you're not really dividing. You are multiplying it with something less than 1. That's the point. So if you multiply this a bar, this pink a bar, with a lambda such that that lambda is 1 by magnitude of this vector, then this pink vector will get resized to the blue vector. Alright, so this is the concept of. So your takeaway is, if you have a unit vector, you can construct any vector in that given direction, and if you have a given vector, you can get the unit vector in that direction. You can do both things. If you have 1, you can get 2. If you have 2, you can get 1. With this, I have a small property for you. Let's say you have m plus n into a bar. So this is a property. M plus n into a bar. What is this equal to? This is equal to m a bar plus n a bar. I will prove it in a short while. Scalars follow distributive property. This m is a scalar, n is also a scalar, this a bar is a vector. Okay, so you are multiplying a sum of two scalars with a vector, and that is distributive in nature. M plus n itself is a new scalar. Okay, m plus n itself is a new scalar, and that scalar is being multiplied with a bar. Then this new vector, so look at this, look at the whole thing. You know, I'm going so slow because you're seeing vectors and scalars for the first time and you have to visualize them correctly. M is a scalar, n is a scalar, m plus n is a new scalar, into a bar is a vector, a bar only is a vector, and this whole thing together is a new vector. And this new vector can be represented as a sum of two vectors, which is m into a bar. A bar is a vector, v is a scalar, m a bar is a new vector, so new vector 1, plus n is a scalar, a bar is a vector, and this is new vector 2. New vector 2 and new vector 1 together can be added to get this whole new vector. So obviously I'm talking about addition of two vectors here. I'm talking about addition of two vectors, something that you haven't studied so far. I have never talked about how do you add two vectors. If you have a number 2 and you have a number 3, you can add them and you can say 5. But if you have a vector A bar and you have a vector B bar such that A's magnitude is 2, B's magnitude is 3, that need not be equal to 5. Why? Because when A bar and B bar are concerned, you just don't have the magnitude, you also have direction. Like A bar and B bar also have their respective directions. And what this sum is going to be, what this A bar plus B bar is going to give you, that sum depends on the direction of A and direction of B also. Whereas with scalars, you don't have a problem of direction. You have 2, you have 3, straight away add them, that's equal to 5. Correct? So here I have two vectors. And before knowing why this is working, why this distributive property is working, I need to know addition of two vectors first, right? That we will do. Now next operation that we will discuss is addition and subtraction of vectors. So you can come back and verify why this is true. But for now, I just want you to note this down as a property. Likewise, there's one more property. So the previous one was the first property, property 1. There's another property. M into NA bar is equals to N into MA bar, and that's equal to M times N into A bar. Again, use the same analogy. Okay, you have a vector A bar. The first part is telling you multiplied this with N, right? So now your vector became NA bar. Considering, let's say your N is more than 0. N can be less than 0 also, but for my example, I'm taking it more than 0 because I want to keep the direction same for visualization purposes. And now this NA bar, which is a new vector, that is being multiplied with another scalar M. So new vector is going to be M into NA bar. Let's look at this guy, the term in the middle. Once again, you had a vector A bar. Now you multiplied it with M first. So this MA bar is a new vector. And then this new vector is being multiplied with another scalar N. So this whole final new vector is NMA bar. Now the point here is this NMA bar and this MNA bar are same. They are equal vectors because they have the same magnitude. As you can see, if this guy is of x units, this guy also will be of x units, and they will point in the same direction. And this explanation is valid even if M or N or both are less than 0, because in the multiplication it will be taken care of. When scalars get multiplied, nothing will change. Okay, and this very same explanation you can give for M into N into A bar also. M into N, M is a scalar, N is a scalar, M into N is a new scalar. That new scalar is multiplied with this vector, and this whole thing is giving me a new vector, and that new vector is the same as this vector because it has the same direction east and it has the same magnitude x. This is how you visualize the proof, and of course mathematically also you can verify, right? This proof you can verify mathematically now itself because you already know multiplication of scalars by vectors, whereas this first property you can't verify mathematically right now because you need to know addition of two vectors first. So let's actually go and study addition of vectors. Now buddies, extremely important, addition of vectors. This is the most operation on vectors that you need to know. Highly important, highly important to have complete clarity about how you take two vectors, how you add them, in fact how you take more than two vectors also, how you add them. Because what will happen in a lot of your physics problems in the future is let me give you a short picture, a short peek into what will come in the future. You will have a box, you will have force 1, F1, you'll have force 2, F2, you'll have force 3, F3, acting like this. And you will study a law which will say the net acceleration of the box is, let's say the mass of the block is m. The net acceleration of the block is the vectorial sum of all forces, of all external forces divided by mass of object. Right now we are not going into studying this law properly because the point is not this law. The point is, why is it that we are studying addition of vectors? As you can see, this is one law which is going to come in your Newton's laws of motion. Very soon it will come. It has many terms. It has the term net acceleration. It has the term vectorial sum. It has the term external forces. It has the term mass. Every term is important. The understanding of why this term is present in the definition is extremely important. So tomorrow when you study these things, make sure you're not studying to memorize the laws. Because if you memorize the law, maybe you can do very basic problems using that. Maybe you can get good marks in your board exams. But when it comes to any question in a competitive exam like JEE Mains, JEE Advanced or BITSAT, you will have to apply this law in a complex problem. That problem will have many aspects, many things which can trap you. And as long as you do not understand the law, you will never be able to crack that problem. So the first thing, your forces have to be external. So this F1, F2, F3, these are external because they are not inside the body. Let's say there is a force inside. I'm teaching a little bit of Newton's laws of motion here, but fine. There is a force F4 which is acting from inside the box. Do you think this force F4 is going to contribute to the acceleration? Then finally, as a result of all these forces, your block gets some acceleration A net, which you have to calculate as a part of your problem, let's say. Do you think this F4 is going to have any impact on the A net? The answer is no, because the definition says the forces have to be external and F4 is inside the body. It's an internal force. Fine, let's not dig too much into that right now. But the point is this definition also has this term, vectorial sum. This is the term that I'm concerned about. Vectorial sum. Which means this definition is telling me I have to take all the external forces, I have to add them vectorially, and then I will get my acceleration. Which means I will have to take, if I were to write this whole thing down, I have to take F1, which is an external force, and a vector also. Force is a vector because it has a direction also. And then I'll have to take the second external force F2. I'll have to take the third external force F3. I'll have to add these three vectorially. And then I'll have to divide this. So this is a vector V1, this is a vector V2, this is a vector V3. When I add these three, I get a new vector V sum, which is my F net. This is my new vector. This F net is a new vector which has to be multiplied with a scalar called as 1 by m times 1 by mass. This is the scalar that I will multiply this vector with, and only then I will get my net acceleration. So the point is, if you do not know how to add the vectors, how will you ever carry this calculation out? How will you get the net external force? And this was just one example in one subtopic of a chapter, wherein not knowing vectorial sum properly will cost you the whole problem. This is going to happen in almost every second or third topic that you study throughout the syllabus. That's why I gave so many stars to this topic. Now that you understand the importance of this, let's go to complete basics. So any vector can be represented using two things, magnitude and direction. Let's say I have vector A. I know its magnitude. Let's say the magnitude of A bar is A, small a. Okay. Let's say I have another vector B. Its direction is known to me because of this angle, right? I know the directions of both because the theta for A is 0 degrees because it's pointing towards east, and the theta for B is, let's say, theta. Again, if you're not understanding this theta notation, please go back and revise Saturday's class. Okay. So I have B's theta, which is theta. So these are the directions of A and B respectively. These are the magnitudes of A and B respectively that I'm going to tell now. So let me color coordinate a little. Oh shit. Magnitude of A bar is A. Magnitude of B bar, let's say, is B. Now with all this data, is it possible for me to add these two vectors vectorially? The answer is yes. How will I do it? To do this, we will use this law known as Parallelogram Law of addition of vectors. Okay, I'm not going to write this law down for you. You can see that on the internet, you can see that from your textbook. My job here is to make you understand what this law is. This law says, if I have two vectors with me, and if I want to add them, then I need to draw a parallelogram such that these two vectors become the edges of that parallelogram. So step 1, I have to draw a parallelogram. You know what a parallelogram is, right? Opposite edges are, parallel. That's a parallelogram. So I have to draw a parallelogram such that, or in fact, not such that, with these two vectors as the edges. That's step 1. And then that's all. Step 2 is diagonal which starts from their tail is the resultant vector. And what I mean by this is, you have joined these two. These two should be joined by tail. And then this fellow, which starts from the tail and is one of the diagonals of this parallelogram that you have drawn, this itself is A bar plus B bar. A bar is a vector, B bar is a vector. When you add these two, you get a resultant vector. That resultant vector also has a magnitude and direction. What is the magnitude of that resultant vector? This length, the length of this green diagonal is the magnitude of resultant vector. What is the direction of resultant vector? The direction in which this green vector is pointing to, that is the direction of the resultant vector, which means this green bar is itself my resultant vector A bar plus B bar. So when you add two vectors, you are going to get a vector as your sum, and that vector is this green vector. Do not get confused with the other diagonal. No, there are two diagonals in the parallelogram, and I'm telling you the diagonal which starts from their tail. So first of all, you have to join these two vectors by the tail and then construct this parallelogram. And then the vector which starts from the tail, that is the resultant vector. This is how you visualize it first. We will also see it mathematically now. Okay. So let's say, let's quickly do a problem to consolidate this understanding. I have two vectors, A bar, whose magnitude is 2 units and direction is 30 degrees, whose direction is theta equal to 30 degrees. Okay, let's write that. B bar is a vector of magnitude 5 units and theta is equal to 60 degrees direction. So and then if I ask you guys, tell me what is A bar plus B bar. When you add these two vectors, what is your resultant vector? How do you get it? Very simple. Start placing them, start drawing them on your graph first. Step 1. Take vector A bar, magnitude 2 units. So draw a vector of length 2 units. So this is 2 units. And your theta should be 30 degrees. This vector is A bar. Okay. Come to B bar. B bar is of length 5 units and theta 60. So your theta will now be double and your B bar is going to be of length 5 units. Right now 2 and 5 are looking the same. That's because of my poor drawing skills. Not so poor also. If you were to attend coaching, your coaching teachers are going to draw much worse than what I am. I personally had to experience that with my teachers. So this is of length 2 units. So you have your vectors available with you. This is the first vector. This is the second vector. You have their directions. Directions are represented using theta. And magnitude is using 5. In fact, not now, but in the future you will see that this A bar will be written as 2 times A cap, whereas A cap is a unit vector which points in this direction. And B bar will be written as 5 times B cap, where B cap will be a unit vector which will point in the spin direction, a unit vector. Okay. So this we will see how we will do in the future. Okay. For now you have them available. So how do I get the resultant vector? First step is to draw a parallelogram with these two as the edges. Okay, so I've run out of space. There's no space on top. So I will have to shorten the length of this B somehow. So this B is of length 5 units. Do not take this, these drawings are not for scale. 5 units. Okay. So step 1 is to draw a parallelogram using these two. Let me do that. And then step 2 is to pick that diagonal which starts from their tail and goes through the parallelogram. This diagonal R bar is the sum of A bar plus B bar. If I know the length of this guy 2 units, if I know the length of this guy 5 units, there is a mathematical formula which we will derive and we will get the length of this also. Okay. And obviously the direction is right in front of your eyes. So we will be able to do it. So right now we are just seeing the whole thing graphically. We have not started with the mathematics, as in we know that the magnitude of A is 2, we know that the magnitude of B is 5. We can see what R bar is, but we don't know how many units. We don't know what this X is. right? We don't know the magnitude of r in terms of numbers. For that, we will have to get to mathematics, and now we will do that. Okay, let's derive the formula for the length of the diagonal. Okay, are you guys convinced? First of all, are you guys convinced that if I can get a formula for the length of this green diagonal, then that formula can be used to get the magnitude of a plus b? Are you convinced? Because this length itself, this diagonal itself is a bar and b, a bar plus b bar. No, so if I can get the formula for the magnitude of, so if I can get the formula for the length of the diagonal of a parallelogram, I can use that formula itself to get the magnitude of a plus b vector. So let's derive that magnitude. Let's derive that formula. Okay, how will we do that? If you have a parallelogram, if you know the length of one edge A, if you know the length of another edge B, if you know the angle between these two as theta, or let me say it's theta dash, because I don't want you to get confused, right? The theta that we have been referring to so far is all about the direction of the vector, like the angle that it makes with the positive x-axis. In most formulas of your textbooks, you will see this also as theta, but this theta is different from that. Even if I call this as theta here, I want you to notice the difference between this theta and that theta. That theta was, if I have a vector a bar, the angle that it makes with the positive x-axis is theta. If I have a vector b bar, the angle that it makes with the positive x-axis is theta. But this theta is the angle between a and b, right? This is not the angle that it's making with positive x-axis. So understand that difference. And now let's try to derive it. So what do we need, guys? We need this blue fellow. We need the length of this blue fellow. So to do that, what we will do is we will do some construction, okay? Which means I will construct a right angle triangle here. So some 10th class mathematics is now going to come into picture. You have A, B, C, D as your parallelogram, and you have a BCE as a triangle, a right angle triangle that I have drawn to derive this blue fellow. Okay. Now, how do we get it? That is the question. So can you guys tell me, if this is theta, then what is this angle going to be? What is angle CBE going to be? Angle CBE is also going to be theta only, correct? Because if you have two parallel lines, and if this angle is theta, then this angle is also going to be theta, no? What are these called? I forgot. These are called as, I don't know. I don't remember the term, but I hope you can verify this for yourself. Okay. The same thing is happening here. You have two parallel lines, AB and BC, AD and BC. AD and BC are two parallel lines, and then you have a transversal AB, right? So theta is, I want somebody to type what these two angles are known as. Corresponding angles. Okay, fine. Right, corresponding angles. Corresponding angles are equal. Fine. Right. Now you guys have also studied some trigonometry. Before trigonometry, what is the length of BC going to be? Length of BC is also going to be B, because in a parallelogram, opposite sides are equal also in terms of length. So look at this triangle, BCE, CBE. This fellow is B, this is theta. I want you to use some trigonometry to get the length of CE and BE. Can we use some trigonometry here? We can. Sine theta is nothing but opposite side by hypotenuse. So CE is nothing but B sine theta. Cos theta is nothing but adjacent side by hypotenuse. BE is nothing but B cos theta. Right? You see what I did there? Just your elementary trigonometry, I'm just using that. I'm just using sine theta equal to opposite by hypotenuse, cos theta equal to adjacent by hypotenuse. I'm just using that. Using that, I got these two. So let me get rid of this now, and let me use what I have just derived. So BE is nothing but B cos theta. CE is nothing but B sine theta. Okay. Now here, I'm going to do something interesting. I'm going to ask you to look at triangle CAE. Triangle CAE. Is this a right angle triangle CAE? This is the triangle that I'm talking about, this outer triangle CAE. Look at it. Triangle CAE is right angled at E vertex. Okay. If it's right angled at E vertex, I can use Pythagoras theorem and I can say AE square plus EC square equal to AC square. Base square plus perpendicular square is equal to hypotenuse square, where your hypotenuse in this case is this blue line which I have to find, whose length I need to find. Your base is AE and your perpendicular is CE. So I can use Pythagoras theorem. I have AE with me. AE is nothing but AB plus BE. Let me go on a different page, it's getting a little shabby here. AE is nothing but AB plus BE. Look at this diagram. This is your AB, which is A, and this is your BE, which is B cos theta. So I'll use that. A plus B cos theta. This is my AB. And do I know what BE is? Well, that is directly visible here. Sorry, do I know what EC is? EC is directly visible here. It is B sine theta. Simply available. I don't even have to do anything. CE is A sine theta. So what will you do? You need, finally, what were you doing all this for? You were doing all this for because you want this fellow, AC. So AC square is going to be AE square plus CE square. AE and CE are both available. So this is A plus B cos theta square plus A sine theta square. Simply open this up. A square plus B square cos square theta plus 2AB cos theta plus A square sine square theta. Take this A square. Oh, sorry, this is not A sine theta, this is B sine theta. The CE is B sine theta. Look at it. It's my mistake. I wrote it wrongly from the previous slide. This is B sine theta, CE. Okay, not A sine theta. So, A square plus, can I take B square common here and I'll get a cos square theta plus sine square theta plus 2AB cos theta is there. You guys would know from your 10th class trigonometry that this fellow should be equal to 1, sine square theta plus cos square theta. So AC square is nothing but E square plus B square plus 2AB cos theta. Correct? So AC is nothing but square root of A square plus B square plus 2AB cos theta. This formula is something that you will have to remember. And I'm not asking you to remember it blindly. I've shown you how it's derived. This is the length of the diagonal. This AC is my diagonal, no? This AC is my diagonal. And I was doing all this drama to get the length of this diagonal. Now, since I have this formula with me, I have the length available with me. Okay? There's one more thing also that you can find. You can also find the angle that this diagonal makes with the vector A. So if this angle is alpha, what is alpha? Alpha is the angle that AC is making with AB. That is your alpha. Can you find that? It's very easy. Once again, you will consider the same outer triangle. You will consider ACE. Okay. So in triangle ACE, tan alpha is going to be opposite by adjacent. Opposite is b sine theta. Adjacent is this thing. AE is adjacent. So AE is nothing but A plus B cos theta. Okay. So alpha is nothing but tan inverse of B sine theta by A plus B cos theta. Don't worry about this inverse right now. Inverse is something that you will study later. But you can get this angle alpha, okay, using this concept. Gunapriya says bye. Bye, Gunapriya. All right. So is it completely clear, guys? I hope you understand how to find the angle that alpha that your resultant vector makes. So we found two things. To summarize, we found two things. If I have a vector A, if I have a vector, like if I have a length A, if I have a length B, and if I want the length of this diagonal R, I need to know the angle between A and B first of all, that is theta. Then I can simply get the length of R as A square plus B square plus 2AB cos theta. And then if I want to find the angle that this R is making with A, then that angle or tan of that angle is B sine theta by A plus B cos theta, or that angle is nothing but tan inverse of B sine theta by A plus B cos theta. Don't worry about this inverse right now. We will look at it later. In fact, when you study inverse trigonometric functions, then you will have full clarity. Then you will have full clarity about what inverse is. But for now, I just want you to visualize inverse as something like this. You guys know that tan 30 degree is 1 by root 3, right? So tan inverse of 1 by root 3 is 30 degree. For now, I want you to imagine it like this. But let me tell you, tan inverse of 1 by root 3 is 30. That's fine. Later you will study more complications about inverses. Are not simple. They are not this direct. There are other complications which are involved with inverses, which means if I say tan theta is equal to x, then tan inverse of x might or might not be equal to theta. In this case, it is valid, fine. But this tan theta equal to x, then tan inverse x equal to theta might or might not be valid. There are many complications. And you are not, right now, this is not the time to discuss those complications. You will study that under inverse trigonometric functions. But for now, you can accept, for now, you can, because you are at a very elementary level. For now, if tan theta is x, then tan inverse x is theta. Okay. So if this thing was root 3, then tan inverse of root 3, your alpha will become 60 degree. Because you know that tan 60 is root 3. Okay. So I want you to memorize these two, but at the same time, I want you to go back and see how I got it. So now let's come back to this problem. Which problem? Wherein I was discussing something about A's length, B's length, and all that. Fine. Okay, if that's not available, let me just quickly frame a problem for you. A bar is a vector which points towards east. This is the direction, and magnitude of A bar is okay. Let's say this is not pointing towards east; it's pointing towards south. It's pointing towards south. Okay, and its magnitude is 5 units. B bar is a vector whose direction is northwest, and magnitude is 3 units. How will you get A bar plus B bar? what will be its magnitude, and what will be its direction, this new vector. Now you can use the formulas that you have just seen to solve a problem like this. Simply, first draw A bar. A bar is pointing towards south, fine, and it has a magnitude of 5 units. Okay, that's not a problem. Let me draw it slightly bigger. B bar is a vector which is pointing towards northwest. Okay, northwest is here. And this fellow has a magnitude of 3 units. Now how will you get A bar plus B bar's length? Very simple. Draw a parallelogram first. With these two as the edges. You have to make sure that these two are joined by their tail, and then throw this vector out which starts from the tail and is one of the diagonals and is along one of the diagonals. This vector is what you are looking for. This vector is going to have some magnitude. How do I get that magnitude? Using the magnitude formula, right? Let's look at that. So this is going to be 45 because this is northwest. If that is 45, then this is going to be 45 and this is 90. So what is the angle between A and B? Isn't it 135? 45 plus 90. So the angle between these two is 135. Awesome. So my job is very simple now. It's very simple. I have two vectors. The first fellow is 5 units length. The second fellow is 3. I know the angle between them, 135. And I want this fellow. I know the formula for this fellow. This is R, let's say. Then magnitude of R, or the length of this diagonal, is simply 5 square, or which is this is A, this is B, and this is theta. Then R square is nothing but A square plus B square plus 2AB cos theta. Just now we have seen A square plus B square plus 2AB cos theta, where A square is 5 square 25, and this is 9 plus 2 into 15, which is 30 into cos 135. Now cos 135 is something that you might not know right now, right? Because right now in 10th you have only studied angles in the first quadrant. Like you know cos, and you know all causes ranging from theta equal to 0 to theta equal to 90. All those values you know, like some basic values. But you don't know angles beyond 90. That you will study later on. Like that's a part of mathematics basics. So cos theta plus 90 is nothing but sine theta. In fact, it's minus sine theta. This identity we can use. Don't worry about this identity right now, guys. So cos 135 is nothing but cos of 45 plus 90, which is nothing but minus sine 45 according to this identity. And sine 45's value, you know, it's 1 by root 2, so it's minus 1 by root 2. And I will simply use that. So 25 plus 9 is 34 plus 30 into minus 1 by root 2. Okay. And this is 34 minus 15 root 2. This is your R square. This is your R square. Okay. Not R. So R is going to be square root of this. So you got the length. Okay. You can do this calculation. You got the length of the vector. And if you want the direction, first of all, you can clearly see the direction. Like you can see it in front of your eyes right now. It's not perfectly southwest. Not perfectly southwest. It will be slightly tilted up or down, you know, from southwest. It will be tilted slightly down from southwest. And if you want, you can get what this exact angle is, right? You can get this alpha. So what is alpha? Alpha is this angle, the angle that this R makes with A. You can get that alpha using this formula. Alpha is tan inverse of B sine theta by A plus B cos theta. Just now we have derived it. You can use this This is your B. Theta is 135. So again, you need to know the value of sine 135. Okay. So you will have to substitute those values and then you can get it. So to do all this, you need to know some trigonometry basics. Like how do you calculate sine of an angle which is more than 90? How do you calculate cos of an angle which is more than 90? Only if you know all that, you can get alpha. But the point is, you can get alpha using all that. So right now we will not dig into how you calculate those, because that's trigonometry basics. But at least you understood the concept that you can get this Brown vector's direction. If you have alpha, you have its direction, because then you have got the theta for it. No, if you have this Brown vector's alpha, then do you not have the theta? You have the theta. Theta is the angle that this vector is going to make with the positive x-axis in the counterclockwise direction. So this is going to be your theta. So you can get theta. Like your theta plus alpha is 270 degree. If you have alpha, then you can get theta as 270 minus alpha. So once you have the theta, that means you have the direction for this arc. And magnitude you have already got using this formula. That's all. You have the magnitude, you have the direction, you have the vector. Did you see? Today was a major jump. Today was a jump from the previous classes. Previous classes were very, very low in terms of calculation and all those things. But now involving stuff is going to come. So if you guys want to follow everything properly in the class, make sure that you have revised all the previous vector lectures. If somebody joins in tomorrow late without understanding today's class, then tomorrow's class also you will struggle. So make sure you take care of all these things, keep your revision intact and keep following with me. And step by step, bits by bits, in every class, slowly, by learning a little, by the end of this bridge course, you would be fundamentally strong with all these principal concepts, right? So with this, I would like to take your leave. Do revise all these things. Make sure you are fully clear. If you have any doubts, you can put in the chat box. I'll wait for a minute and then I will leave. Looks like there is nothing coming. That's fine. Thank you, Akshat. So I will take your leave now. Take care, guys. Bye-bye. See you tomorrow.